Good morning, good afternoon, and good evening, everyone. So today we're going to be talking about maximum and minimum values in 3D. So before we used to talk about this, well, at least in my previous courses, we did talk about what is a minimum, what is a maximum given a real valued function, right? So let me just actually briefly talk about that since we didn't really, I haven't posted any calculus 1 and 2 videos. I did, but like it's really surface level. So when we look at, yeah, I remember I didn't talk about minimum or maximum in calculus 2. Yeah, it was only in calculus 1. So in calculus 1, let's say if we're given y equals f of x, and here we say that's a real valued function. Let me charge. That's a real valued function. Um, Say we're given a curve. Uh, Something like this. Something like that. Now, where would be the maximum value? Well, obviously, it's this one. Where's the most or the minimum value? Actually, I shouldn't have just done this. Oh, I erased the whole thing. Let's just say it's here, right? So this is the maximum, absolute minimum. Let me go ahead and say. So this is the absolute maximum, and then this is the absolute minimum. And we also have this idea called a local minimum and a local maximum. This is one of those local minimums. This is a local maximum. Now, fun fact, this is also a local max. This is also a local min. So there are local maxes. There is a local max. That's an absolute max. Oh wait, what's the saying? Local maxes can be absolute maxes, and local minimums can also be absolute minimums. But not all absolute max and mins can be local max and mins, right? If you get my what I'm saying. Yeah, that's the idea, right? So that's calculus 1. There's a more mathematical definition of it, like here we say that f is continuous. That's why we say this is true, and something like that. But yeah, I'm not gonna dive deep into that. I'm gonna go directly to our topic. I just realized, am I sharing? Okay, I thought I wasn't sharing the right screen. There was a previous video, I think it was partial derivatives. I did not share my screen at all. Anyway, so let's talk about local in calculus 3. So we have local max and min. So what's local max and min values? Well, if we, I don't know if you guys read chapter 4. I'm not gonna say it though, because I did not read chapter 4. But one of the main uses of ordinary derivatives, we're talking about like calculus 1 derivatives, not two variables. It's just a single variable. Finding maximum and minimum values are what we call extreme values, right? That's the purpose of getting derivatives, right? So how do we know? Right here, right? How do we know how can we make use of derivatives? Well, again, when we take the derivative of something at a point, we get its tangent line at that point, right? We get the slope, right? See that? But then what if we get, let's say, what if we get, let's say, the local max or the local min? Well, what do we notice? If we get their derivatives, all the tangent lines are horizontal lines. What does that mean? That means our derivative has a slope 0. And so if we're given a function, we take its derivative, make it equal to 0, and then we can find we can find the local maximum and minimum. But now here's the big question. How do we tell? How can we tell if it's a local max and min? We'll see that later on. But it's more on analyzing the graph pretty much, like where it came from. So intuitively, how would this be? We're going up here, and then we're going down here. And then there's a slope. If we're going up, then down, that's a local max. Now here we're going down, and then we're going up. What is that? We're going down, we're going up. Oh, that's a local min. And same idea. We're going up, down, local max. Down, up, local min. Up, down, local max. Down, up, local min. Up, down, local max. Down, up, local min. Right? So that's the idea. But mathematically, that one's going to be getting an interval and then analyzing or plugging in values, checking if it's a positive, the derivative. If it's increasing, then decreasing. Anyway, we'll get into that in a bit. But now we're going to look at it in 3D. So here in this section, we talk about how to use partial derivatives this time to locate a maxima and minima of functions of two variables. So when we say maxima and minima, that's the same as maximum and minimum. I don't know why they... Anyway, in particular, in example 6, so guys, just take note of example 6. We will see how to maximize the volume of a box without a lid if we have a fixed amount of cardboard to work with. Okay, we'll take note of that. Okay, so here let's actually look at the values in the graph of f shown in figure 1. So let me look at figure 1. I will quickly take a screenshot and paste it. There. So what is this? Oh, look at that. It has some humps. What do we see? We see some maximums, minimums. We can see if it's local or absolute. I'm highlighting, I'm trying to do a color thing. If it's local, it's blue. If it's absolute, it's red. Something like what I did here. And so if we get their partial derivatives, we actually have two partial derivatives. One with respect to x, one with respect to y. And yeah, we pretty much get horizontal tangent lines. And so we get from there horizontal tangent plane. Right? So we're kind of building stuff here. Let's look at that. We have 2 points, A, B, where f is a local maximum. That is where FAB is larger than nearby values of f, x, y. So here we actually have two local minima, where FAB is smaller than nearby values. The largest value of f, x, y on the domain of f is the absolute maximum, and the smallest value is the absolute minimum. Right, so let me just dissect what I just said there. So here we have 2 points A, B, where f has a local maximum. Where is that? 2 points A, B, where f has a local maximum. But it's talking about this one and this one. Remember how I said a local can also be an absolute, but an absolute can never be... Wait, a local... No. Uh, all... Okay, forget what I said. What I'm saying is that a local can be absolute, basically, right? So these are both FAB, right? They both have a local maximum. So both of those are local maximum. The absolute maximum is also a local maximum. Okay. And then We also have two local minima. So here, the textbook used minima. I would just use minimum. Maxima and minima are the same as maximum and minimum. Like it doesn't matter. Then we also have two local minima, right? Where's the local minima or minimums? I just said we're not going to use minima. These are the two local minimums, right? What else? The largest value of fxy is absolute value. So that's the largest one. So this is the largest one. This is the smallest one, right? Okay, so let's do a definition. So for my definition here, we're being, okay, so we have a function of two variables. So f of xy, we're assuming here, and we're saying it has a local maximum. And let's do it at some point AB. If my function is less than or equal to that output, right? So that's the mathematical definition. We're saying if there is a local max, if in particular my output is greater than most of my points in that quadric surface, right? So this means, oh, I haven't completed it. When xy is near AB. So we're saying at points near my AB, if those points are less than or equal to my AB, then we have a local max. So we have a couple of points here, couple of points here. Those are my xy's. And then my blue point, that's my AB. These xy's are near AB, but AB is greater than or equal to these points. And so we say that's a local maximum. And similar to here, bunch of xy points that are near AB, but we say, oh, there's the bigger point, this red one, and we say that's also a local maximum. That's the maximum, that's the mathematical definition. But now that is weird, right? Because we know we want to be precise. What do we mean when we say near? So that one's a, what is that? What is near? What does that mean? Well, that means my, so when we say near, my f or my set of outputs here should be less than my maximum value for all points y in some disk with center AB, right? Okay, now we're trying to be a bit more precise here. What do we mean when we say near? Well, we mean this. Oh. But then again, this is still not kind of precise and according to the textbook, because how do we explain what this disk is? Is this a something we can define using a contour map? Probably, right? Because we can use that to measure quadric surfaces. Is it? I can't really tell, to be honest. I don't know what this disk is, but I'm just gonna leave it here because it looks like this is important to know. Um, so yes, that's called the local maximum value, right? Okay, and then from there, actually, wait, is there a way we can write this? Local max at AB if it's fine. I'll leave it at that. So this is called the local max. Okay, I guess I can't. So that's a local max. This whole thing is a local max. I'm actually gonna erase this because I don't want the definitions to be too long. I want it to just like make sense. So this is local max, right? Let's keep it intuitive. And then uh, if my set of xy points are greater than my output of AB, when xy, so we're going to use that near thing again, is near AB, well then that's our local min, right? Okay, so there is some proof. I might not get into it anymore because this is a bit weird. Find extreme values, second derivative tests. Okay, so I have to get onto example 3 to go to the exercises. Okay. Let me go ahead and go to Fermat's theorem. So this is something. Oops. Okay. I hope that didn't. Was I able to draw there? Oh, okay. Um. Okay, let's get into Fermat's theorem. You might have probably heard of this. At some point. But if not, then I'm just gonna say it anyways. So what does Fermat's theorem say? For single variable functions, so f of x is one of them, because you only have a single variable in the function. I like how they make it sound kind of obvious. So if you read math, it's kind of obvious what it is. Um, if f has a local max or minimum, okay, here's the theorem. If f has a local max slash min, local maximum or minimum at C. So we're gonna say at some point C, and if its derivative exists, oh, then what we defined earlier, then its derivative at that point is zero, right? We did look at that earlier here. So these are examples of C values. So these X parts, right? Those are when the derivatives are zero. Their slope is zero. So that's Fermat's theorem. Uh, and now we have another one, this time for functions of two variables, right? Obviously, there's going to be one for single variable and one for multivariable. So here we're saying if f has a local min. Okay, now I switched it up. Max or min. And we're going to say it's at the point AB, right? Because we have 2 points. And we're saying the first order partial derivatives exist. So that's f sub x and f sub y. Then we're going to say both of their slopes are zero. Both of their tangent lines are zero. So f sub x at this point. Let me write this here because this is nice. F sub x and f sub y are actually both just equal to 0, right? Just like how I previously did here. These are both horizontal slopes. They're just basically flat there. One's in terms of x, one's in terms of y, right? Okay. The proof for this, just to be mathematically precise, I'm not gonna get into it. Um, yeah, I'll not get into the proof. I'll I'll focus more on intuition here. Okay, let me do example one. I like going to the examples. Oops. Because I don't want to talk about proofs too much. I'll do that when I'm in a class of proofs, I guess. But right now, no, I'm not. Um, Still learning the intuition, kind of. Okay, let's go to an example. Here we're saying that we let f of xy be equal to x squared plus 2y, or y squared minus 2x minus 6y plus 14. Okay, they actually gave us the partial derivatives here. So my f sub x is 2x minus 2. How do I know? This is 2x, 0, 0, 0, minus 2. Done. 2x minus 2. And then my f sub y, this is 2y minus 6. And then these partial derivatives are equal to 0. So if we set them equal to 0, we can find the critical point, right? When I mean by critical point, we can find the critical point, meaning it's either a local or an absolute maximum or minimum, right? So I'm going to say setting these to 0 helps us find critical point slash s. Could be more. Depends, especially if you have a quadratic one, right? Because we get 2 points there, or a cubic one. If we set these to 0, right, then we should get, I believe this is x equals 1, this is y equals 3, right? So those are our two critical points. And there we have it. We've actually found that part. Okay, so the textbook is telling me to complete the square. Um, if we do complete the square, so that's an algebra thing, then we get this value. 4, I think this was a plus. Look at that. There's my 1 and 3. And I think we could have gotten this without taking their derivatives. If, let me see, could I have gotten them without taking derivatives? I'm also a bit curious. This one's a 14 though, so how? Oh, because he did complete the square. This one's x minus 1 squared. But then I have to add the minus 1, I think. I'm not sure. 2x plus 1. Oh, so I have to add the minus 1. So this was a minus 1. So this thing is that. And then I added to, again, well, this is y minus 3. And I think this one gives me minus 6y plus 9. Oh, so this one's plus 9, right? I'm trying to see. Plus 9 plus 1. Yeah, if I get the completing the square, this one gives me x squared minus 2x plus 1. This one gives me y squared minus 6y plus 9. Oh, and then I get 10 plus 4, I get 14. Okay. 9 plus 1 plus 4. That's where I get the 14. Cool. Okay. Yeah, this is the completing the square one. Okay. And then from there, what? Yeah, so I could have gotten it anyways without taking derivatives. Um, because I mean it's there, right? 1, 3. So since my x minus 1 squared is greater than or equal to 0, as well as my y minus 3 squared, and we have f xy is greater than or equal to 4 for all values of x and y. Doesn't make sense. Mm, actually, no, it does make sense. It does make sense. And so we have 4 as a local minimum, and that's the absolute minimum as well, right? So here we have, since we're saying that my x minus 1 squared as well as my y minus 3 squared are both greater than or equal to 0, then I can say uh, this point here that's equal to 4, or no, that's greater than 4. And this applies to all values of x and y. Then my function that's equal to 4 is a local minimum. That's also an absolute, right? So yeah, that was the idea. We take the partial derivatives, we set their derivatives to 0, we get the critical points, and then we find out whether it's a local max or local min by completing the square. That's one technique, right? Let's look at some more problems here. Oh yeah, I'll give the visual actually of what this surface looks like. It's actually an elliptic paraboloid. And we can tell just from taking out these numbers, right? If we take out my z, I'm not gonna do it right now. Take out my z in my xy, I should get an ellipse. Or no, I should get a circle actually. Some circle. And if I take out my x, I get a parabola. If I take out my y, I get a parabola. So it's some circular or elliptic paraboloid. So that's the idea. We take out the variables, we check if, and then we isolate them. We check their trace in that specific plane, and then we'll get the thing. Okay. Next. Hope that makes sense though. Okay. For example, two, Yeah, this is more, it's not even more on computation. This is more about like visualizing, not even visualizing, I think. It's just identifying the max and min of a surface. So here we're being asked to find extreme values. When we say extreme values, we mean when is their derivative zero? In this case, in 3D, when are their partial derivatives zero? And so we're given this function of a quadratic surface. And here we can already see this looks like a hyperbola. It's a hyperbolic paraboloid, right? Okay, so what's the idea? We take partial derivatives and set to zero, and we're done. That's how we get it, actually. So we just get their partials. Well, in this case, this is what? Minus 2x, 2y. Then we get there, we set them to zero. X is zero, y is zero. And so those are our critical points. We're actually done with that, right? But notice that for points on the x-axis, we have y equals zero. Let me actually just show the graph of what in the world this looks like, just so that we can see what the extreme values look like. Here's the graph. Here's what it looks like. And there's our critical point. Here we can see that in the x-axis, we have y equals zero. And so our f of xy, when it's equal to negative x squared, is less than zero, right? So we're looking at this one. It's a downward concave down. That's when negative x squared. If we take out my y, we set y to zero. We set this to zero. We get z, so this is z, right? Negative x squared. So if you look at the xz plane, let me try to draw this. Zx, this is that parabola from the xz plane, right? What else? I'm just trying to like gather ideas here, but the textbook is mostly just characterizing the graph. However, for points on the y-axis, we have x equals zero, and so my y squared is greater than zero. So here now it's different. If we look at the yz, well, here you notice this is a concave up parabola or trace, right? Thus, every disk with center 0, 0 contains points where f takes on positive values as well as points where f takes on negative values. So we do have positive f values and negative f values. However, so here's the case. f(0, 0) can't be an extreme value for f. So f has no extreme value. Why is that? So here in this case, this is not an extreme value. So we're saying that a big but. Okay, don't clip me. I meant a big however. This one, f(0, 0) equals 0, is not an extreme value. So meaning there is no maximum and minimum here. And that's the idea that there is no maximum. I just said it. There's no maximum or minimum at that critical point. And so this is one way where it can happen, right? uh, Yeah. So if we look at it from the direction of the x-axis, it's a maximum. But if you look at it from the direction of the y-axis, it's a minimum. So we actually kind of have to look at it in two ways. If we look at it from the perspective of the YZ plane, it's gonna look like this. And we can see that's a minimum here. But if we look at it from an XZ perspective, well, now it's a maximum thing. So in other words, even though we have the extreme value or the critical, no, we don't even have the extreme value yet. If we get the critical points, we really have to identify if it is indeed a local or absolute max and min, right? Okay, so recall that for functions of a single variable, we have a critical number C, where f prime of z is 0, and this may correspond to a local max or min, or neither, right? An analogous situation occurs for functions of two variables. So we have a similar situation. If AB is a critical point of a function f, where its partial derivatives are 0, it may be a local min or max, or neither. In the last case, we say that AB is a saddle point. Actually, yeah, that's the saddle point. So if it's neither a max or min, we call our critical point a saddle point. Why? Because it looks like a saddle. When you ride a horse, you ride a saddle. The horse has a saddle. Kind of looks like that. So they just named it a saddle point. I don't know. Okay, so the name is suggested by the shape of the surface in. Okay, so the surface is the hyperbolic paraboloid near the origin. In general, the graph of a function at a saddle point need not resemble an actual saddle, but the graph crosses the tangent plane at that point. Okay. So we need to be able to determine whether or not a function has an extreme value at a critical point. And so the following test, which is proved at the end of this section, is analogous to the second derivative test for functions of one variable. So, okay, so last time when we did this, we couldn't determine on our own, right, if it has a local min or max. So here's the other test we can do to determine if it is indeed if it is indeed an extreme value. And so that's the second derivative test. So we take their second derivative and then we check, right? So let's just go through it actually. Um, so okay. So we couldn't check it here. Now we're able to check it. Derivatives. Right? Um, let's give a scenario. So suppose the second partial derivatives of f are continuous. So here's what we're dealing with in this intro calculus courses. We're going to be dealing with continuous functions. So it's continuous on a disk with the center. So we did mention about centers. The center is that point AB. And suppose that point, when we take its partials, are 0, right? So now we've determined, okay, that's a critical point. right? If we find that they're equal to 0, that's a critical point. So now we let d for derivative. Actually, I should have just done this. We let let me see, the derivative of AB. Oh, so that's what they mean by second derivative. It's a capital. So we're looking at their double, I'm going to call it a double x because I don't know what else to call it, right? So if we take the derivative twice with respect to x, we multiply it to the fyy, and then we subtract it to the fxy, which is the same as yx because of Clairaut's theorem, right? And we did talk about Clairaut's theorem in a previous video. And we actually square that. So here's the condition. If my d is positive and my fxx, okay, now this will help us determine whether it's a max or a min. And let's say my fxx is greater than 0, then it's a local minimum, right? Yeah. And then if my d is greater than 0, but my xx is negative, then it's a local maximum. Oops. So it's a local maximum. And lastly, well, the case where my second derivative is just negative. It's a saddle point. So if we go back to the previous thing, and if we take this d, it's probably going to be a negative because it was a saddle point. So it's this case where there is no minimum or maximum. It's just a saddle point. Okay. That's the condition. I'm going to stop right here because I don't want the video to be too long. I'm going to proceed to the next exercise in a bit. Yeah, I hope you guys enjoyed, and I'll see you all in the next one.